Yes. So first of all, thank you very much for the invitation to speak at the MES again. And a special thanks to the organizers, Bardzo dziękuję. I'm really sad that I couldn't come to Warsaw, which I really would have liked to see, as I haven't so far. I'm talking about the electronic structure of atoms and molecules in strong magnetic fields and their implications for the detection of stars. And I would like to start with talking about what I actually mean by a strong magnetic field. So the human brain has a very weak magnetic field of just 1 picotesla. This is something that we encounter on Earth. Other weak fields would be the Earth magnetic field, the refrigerator magnet, 4 millitesla. And then we come to a bit stronger fields like the NMR machine, 12 Tesla, or levitation of the frog, 16 Tesla. But this is not the end of the line, so you can go even higher. The strongest non-destructive magnet is in the Los Alamos National Lab and can generate a field of 100 Tesla. And then inside of the Z machine, there exists a field of 10,000 Tesla, but it's not all that accessible. Okay, so when we talk about magnetic fields and strong magnetic fields, it's useful to speak in terms of the atomic unit of the magnetic field, which corresponds to about 200,000 Tesla. And then it's a bit natural to distinguish 3 regimes, namely the Coulomb regime, where the magnetic field is much weaker than the atomic unit, then the mixing regime, where they are about the same order of magnitude, and then the Landau regime, where the magnetic field is much, much stronger than the atomic unit. And now if we convert the numbers that we just saw on the slide before to atomic units, then we see that maybe except for the Z machine, everything is in the Coulomb regime. But this is different when we go into space. There are compact stars that have magnetic fields, for example, magnetic white dwarf stars. And they have fields up to 100,000 Tesla. This corresponds to about 0.4 atomic units. This is certainly in the mixing regime. And then even stronger fields do exist. For example, on neutron stars, 100 megatesla up to 400 atomic units, and special neutron stars called magnetars, where up to 100 gigatesla exist. And this is certainly in the Landau regime. White dwarfs are very interesting. They are also extremely common because 97% of all stars become white dwarfs when they die. So will our sun eventually, often going through a phase where they have this beautiful planetary nebulous. And then in the end, you end up with a white dwarf, which has no nuclear fusion anymore. They are very dense. You can think of them being as big as the Earth, but as heavy as the sun. And in their atmospheres, you typically find hydrogen, helium, and then what astrophysicists call metals, which is everything that is heavier than helium. For example, carbon, silicon, and so forth. And even molecules, H2 has been detected. There have been seen CH bands in the spectra, C2, and so forth. When they got older, they cool down, and effective surface temperatures range between 4,000 Kelvin and 150,000 Kelvin, but usually more between 8,000 and 40,000 Kelvin. The closest white dwarf that we know is Sirius B. That's on this picture, the little dot here where the arrow is pointing to. The big one, that is Sirius A. And this is Sirius B is a white dwarf and the first one that has been discovered and has been studied quite extensively. Then 10 to 20% of white dwarfs are magnetic, which is a very large number. As I said, the magnetic fields range up to 100,000 Teslas, which is 0.4 atomic units. And this is what I call in this context a strong magnetic field. In this regime, hydrogen and helium have been detected in the atmosphere. For the low fields, the situation is somewhat similar to the non-magnetic white dwarf. But it is quite reasonable to think that this is because there are no real predictions beyond helium. And I will show you how complicated these things get. This is an example of a spectrum taken from a white dwarf. This is something that is a bit rare because this is phase resolved and in the UV range. This is from the Hubble telescope, most of these spectra are taken in the visible range and do not have that sort of precision or being phase resolved. You can see that the spectrum changes. That's because the magnetic field is not the same at all angles. What we typically use in order to assign the spectra are so-called lambda curves. And the information that is in this lambda curve is essentially the excitation energy as a function of the magnetic field. So imagine you have an excitation energy for a given transition, and then you look what it looks like as a function of the magnetic field. And then in the lambda curve, you plot it the other way around. So magnetic field against excitation energy. And then it's typically plotted not against the excitation energy itself, but instead the transition wavelength. So the curve would be mirrored. And then what you will see in the spectrum is when the excitation energy doesn't change much with the field. And that would mean in terms of this curve that is relatively vertical. Or you would see absorption dips at this inflection point. Typically from telescopes, we have spectra in the visible range, so between 4,000 and 8,000 angstrom, and UV and IR spectra also exist, for example, via the Hubble telescope. This is a typical example from a spectrum from a strongly magnetic white dwarf, and this is hydrogen. In the upper panel, you see the spectrum, and in the lower panel, you see the lambda curve. And what you're really seeing here are the Lyman transitions. And where this absorption dips now hit the lambda curve, this is where you can then read off the magnetic field. And in this case, it is 185 megagauss that corresponds to about 18,000 Tesla, so quite strong. Most of these spectra have been solved in the 70s and the 80s, and things are quite more difficult when you have two electrons. So this is a famous example of CD229, which has a helium atmosphere and has long been not assigned to spectrum. And it could only be assigned because of the full CI finite field calculations on helium done by Becken and Schmelzer in the late 90s. And here you can see that the curves are much more complicated. So in the spectrum before, you saw that in the lower field, you have this linear splitting, linear Siemens splitting, and then you see the quadratic behavior, but it's quite clear. And here we have lots of essentially avoided crossings, and these, therefore the curves are quite difficult. And in this case, you can only assign a magnetic field range, which would be here between 30 and 70,000 Tesla. So we have also said that the magnetic white dwarfs are in the mixing regime. And here we can ask which atoms or molecules exist in such strong fields. And this has implications for astrophysics and observational spectra, of course. And the other question would be, what is the chemistry in these strong magnetic fields? And both questions can be addressed using quantum chemistry. And since in this regime, the Coulomb and magnetic forces are of the same order of magnitude, finite field methods should be employed, because perturbation theory, unfortunately, no longer works. And when you have these methods, you have a seamless transition from the field-free case to, in principle, any field strength. The molecular Hamiltonian that we're then dealing with is the one given here. So you have the non-relativistic many-electron Hamiltonian H naught plus some additional terms, linear and quadratic, in the magnetic field. When I put the field in a z direction, then I get this simplification down here. Here it is again. And because of the angular momentum operator in one of these terms, the wave function is in general complex, which hence requires new software implementation. And in addition, the Hamiltonian is gauge origin dependent. So for the results not to be gauge origin dependent, we have to use gauge including atomic orbitals or London orbitals, as they're also called. So the first term here is the orbital Zeeman term. This is the term which is responsible for splitting the orbitals. So for example, the p orbitals would be split such that the p-1 orbital is stabilized and the p+1 is destabilized, while the p0 is essentially unchanged. And similarly, in the spin Zeeman term, the degeneracy of alpha and beta spin is lifted, which hence leads to a favorization of high spin states. for stronger magnetic fields. And then there is the term which is always destabilizing, while the first two can also lead to a stabilizing effect. The diamagnetic term is always positive, it's the harmonic potential, as you can see in the confinement of the system. In the literature, there are many finite field methods around, and finite field methods are currently quite popular. There's a lot going on. There's Hartree-Fock theory, 4-component, even RPA excitation energies, CAS-SCS, there's EFT, there are full configuration interaction methodologies going on. For Hartree-Fock and DFT, at least when the aim is to predict spectra, the capabilities are a bit too limited because we don't know enough about the accuracy. For full CI, of course, that's the perfect method for it. Unfortunately, it's also quite expensive and not really applicable beyond 3 to 4 electrons. And hence, the goal was for us to develop accurate methods for heavier systems. And hence, we did coupled cluster and equation of motion coupled cluster developments with finite fields. In equation of motion coupled cluster, there are different variants that you could go for. For example, the one that is very well known, where you have electronic excitations from a given wave function. Then you can remove an electron, you can add an electron, and you can flip the spin. And with this, you have, of course, access to many different kinds of states. And in our work, we have done from a little bit of this toolbox in terms of coupled cluster and EOM coupled cluster development. I want to show you as an example the investigation of sodium, which came to pass because on an astrophysics conference, I was shown this set of spectra, and this set of spectra all have a similar feature. And the similar feature could be a strong transition of one particular element, but with different magnetic fields. And the question was whether this could possibly be sodium, because sodium has a strong sodium D line, which is also seen in the weaker magnetic field. And hence we have looked at sodium in a strong magnetic field. So what you see here are the total energies of the sodium ground state and some excited states. For example, the states where the p orbitals are occupied, green, red, and blue. And with these states, now we can calculate the excitation energies, and from this calculate the transition wavelength. And if we have this information as a function of the magnetic field, we can predict the lambda curve. So this would be one example for the transition from the 3s to the 3p orbitals. So they're essentially the sodium D line without spin orbit coupling. And you would see that, of course, you know very well from the weak field limit that you have this linear Zeeman splitting. And for stronger magnetic fields, of course, it becomes more complicated. But we have this line in the middle here, which is rather stationary. But we have also looked at not only this transition, but many more. And then this the lambda curve actually became a bit crowded. And hence we have looked at intensities. So to only look at states or state transitions that have intensity. And for this, we need the dipole oscillator strength. And the dipole oscillator strength here has the square transition dipole moment, or STMs. And in order to calculate these, we need transition dipole moments. And within equation of motion coupled cluster theory, in order to do this, we also need to solve for the left-hand side EOM equations to generate this transition density. But when we have this transition density, we can then contract it with dipole moment integrals, and with this get transition moments, and from these calculate the squared transition dipole moment, or the STMs. And this is what we got So you can see that, for example, for the stationary transition that I shown you before, the 3s to 3p north, this is the red one. This is relatively constant. If anything, it is increasing in the magnetic field. So this is something that should definitely be seen in terms of intensity. And there are some lines that simply go down and have a not so complicated structure, and some do have a quite complicated behavior. And all the ones that have a complicated behavior have one thing in common, namely that these are transitions that involve the 4s or the 3d north orbital, or if you think about it, this is really a sigma G orbital, because in the magnetic field, the atom has C infinity H symmetry, and then the s and the d north orbital are both of the same symmetry, namely sigma G, and hence this neon 4s and neon 3d north states are both doublet sigma states, which are not distinguishable and which may not cross. And when we go back to this plot of the energies, then this is also what we really see, namely here, these are these two states that I just mentioned, and they go through avoided crossing here for something smaller than 0.1 atomic unit. And these are really all the states that have this rather complicated behavior, and hence this avoided crossing being there makes this make these curves of the transition dipole square transition dipole moments quite complicated, and hence you can really say that no prediction is possible without such a finite field calculation, not even qualitatively. So you really have to calculate it. There is another point to make, and that point is accuracy. If you assume that at the EOM-CC level, your error would be 0.1 eV, and now all the coupled cluster people know that this assumption is actually a quite optimistic one, and the error can be easily more at the EOM-CC level, then if we assume such an error and calculate what kind of difference that would make in terms of error in angstrom in the transition wavelength, then in the UV range, it's not so bad, +8 angstrom, but in the end of the visible range, the error would be something nearly 500 angstrom. And that means that if you're aiming for an error of, say, 50 angstrom, 50 to 100 angstrom or less, then we really need to bring down the error by 1 order of magnitude. And for this, in order to do this, we can go and implement also triple excitations, and this is exactly what we have done. So we also implemented EOM-CC, and then for that particular application, we used extrapolation scheme. So we calculated the triples at the lower with a smaller basis set, and did the basis set extrapolation, and also used a shift to set the numbers that we get equal to the very, very good predictions from the NIST database at b equals 0 at the field-free case. And if we do this, then we get the curve that I'm showing here. So this is now a selection. You see again the 3s 3p transition to the sodium D line plus some 3p 3d transitions. But I'm also showing what you would get if you just did your EOM-CC and the triple zeta basis. And this is actually quite interesting, because if you look now at the, or let's start at the left. So here, if you do CCSD with triple zeta, quadruple zeta, or this basis set extrapolation with triple excitations and everything, it's quite converged. So the differences are not that big. But on the right-hand side, there is quite a big difference. So with a smaller basis set, you would think that you get a relatively vertical B lambda curve for this transition, 3p north to 3d minus 1, while after the extrapolation, we see what you would rather expect, that this transition is blurring out. Yeah? And if we look more closely to the transition that we really expect to see in the spectrum, because it's so strong, the 3s to the 3p north transition. So this is a zoom of only this transition at the 3 levels of theory. Then we see that this transition actually gets more vertical when we do the better calculation, I would say. And hence, this transition definitely should be there. And what I've shown here is where these moving peaks that I showed in the beginning in the motivation in the spectra were appearing. This was between 6,500 and 7,500 angstrom, more or less. And here we don't have anything. So this strong SP transition is not in the right range, and it should be visible at about 6,000 angstrom. So we can at least say that this example is not sodium. Another example that I want to show are molecules in the remaining 5 minutes that I have. And here we have looked at lithium hydride. Because when you look at molecules, then you have an added complication. And the added complication is that the magnetic field, that the direction of the magnetic field with respect to the molecules now matters. If you have just a 2-atomic molecule, then you have difference between the parallel orientation and then any angle up to the perpendicular orientation, which would be the 2 most extreme cases. And they also have a different symmetry. So the parallel case would be C infinity and the perpendicular case would be CS. And this is the ground state plus some excited states in this symmetry. And what you can see is that there's actually quite a difference in energetic between these 2 orientations. And not only that, if we now look at the transitions and the square transition dipole moments in order to predict intensities, then in the parallel case, we would see that all these possible transitions actually decline in intensity. And now in the perpendicular case, we get a very complicated behavior because here, again, there are many avoided crossings. And in any instance where you find this avoided crossing, there these curves actually become rather complicated. Also, because the symmetry is lower, additional transitions are of course allowed. So we can conclude that the square transition moments are extremely sensitive to state interactions, and there is no estimate possible without a calculation. And that was true even for atoms, but you can see it here even more clearly for molecules. Then the last example that I want to show again deals with the accuracy, namely the accuracy of doubly excited states in a strong magnetic field. And here I'm showing the example of the CH+ molecule and 3 excited singlet states. So the field figure round state is singlet sigma. I have 3 sigma orbitals doubly occupied. And then the red state that I'm showing is where I put the electron in the pi -1 orbital. Then I have the corresponding pi +1. And I have a state that is in yellow, which is then even more stabilized by the orbital Zeeman term, where 2 electrons are in the pi -1 orbital. And this state, the yellow one, is doubly excited with respect to the sigma ground state. So from the 3 sigma orbital, 2 electrons have been promoted into the pi -1. And the coupled cluster experts know, of course, that the doubly excited states are more difficult to describe well with, describe well. So in this example, now I'm showing the difference between EOM-CCSD and EOM-CC-SDT results. And as you can see, the EOM-CC-SDT results still have the dotted lines. That for the states that are not the one with the double excitation character, these are quite similar, essentially on top of each other, while the delta state, the yellow one, is quite different. And actually this crossover point is different by 10,000 Tesla, so quite a large number. And in addition, also this shift is not even constant, but it is not even parallel, but it is changing with the magnetic field. So the error that we see between now CCSD and CCSDT, the difference for the doubly excited state at the CCSD level is something like 40 millihartry, while if I calculate it at the CCSDT level, it comes down to where the singly excited states are at EOM-CC. So we really get the error then down 1 order of magnitude, which is good. And if we compare now also, so on the left-hand side, this is the curve that you've seen before, and on the right-hand side is now a comparison against full CI. We see that now these are really essentially on top, and the CCSDT result is really good. Now, the last point that I want to show is that what I've shown you this far was the parallel orientation, and in the parallel orientation, is actually the simplest, because if I look now at the skew angle of not 0 degree, namely parallel, but instead I change the angle between the magnetic field and the molecular bond to 30 degrees, then I'm losing all the symmetry, have C1, and now I can see that actually the double excitation character is moving between the yellow state and the blue state, because the crossings, the former crossings in the parallel case, they become avoided crossings, and then the double excitation character moves between these states. Yeah? So depending on where you are in terms of magnetic field strength, the state can have more or less double excitation character acquired from an avoided crossing. And you see the same thing at different orientations as well. So this double excitation character can move, and hence the accurate description of everything is of course crucial. And with that, I want to summarize. There are challenges in the prediction of spectra from highly magnetized white dwarfs, namely the field strength is unknown and the species is unknown. And we can use finite field methods to investigate atoms and molecules in strong magnetic fields, but we really need high accuracy to do so. And the electronic structure is really very complicated because of these avoided crossings, and that is true even for atoms. Hence, often not even qualitative predictions are possible without the calculation in the mixing regime. And with that, I would like to thank the people in my group, Florian Hampe, who was my PhD student and now is a postdoc with Anna Krylov, Niklas Groß, who was a master student with me, Petros, who is a PhD student now, Simon and Sophia, who are master students, and then the whole theoretical chemistry group in Mainz, as well as Jürgen Gauss for good discussions, but also the freedom to he gives me to pursue my own science, and the DFG for funding, and of course you for your attention.
Thank you very much. Thank you for staying on schedule. There is a time for questions now. If not, I have one question.
Yes.
You mentioned LIH molecule.
Yes.
This is a four electron molecule which can be treated quite accurately with explicitly correlated functions. What methods have you been using in your calculations?
So in the LIH example, we have been using EOM-CC. So I've shown you yes. So yes, so this was at the EOM-CCSD level, EOM-EE-CCSD level, and that's because this is work where we have also calculated the square transition moments, and for these we had to also solve for the left-hand side. But of course, in principle, so we could also calculate that using EOM-EE-CCSD.
Yes, thank you.
Jacek.
Yes.
I have a question. I tried to raise hand. Can you hear me?
Yes, we can hear you.
Okay. So my question is for these diatomics. is it necessary to consider the change of the internuclear distance with the magnetic field?
Yes. So this is an interesting point. So what we see is that the magnetic field sort of squeezes the bonds, and typically what you see is that with a stronger magnetic field, the bond distance shrinks, and this is also dependent on the orientation of the magnetic field. But in these cases that I've been showing here, the bond distance actually in the CH plus example, the bond distance was kept constant. In the LIH example, the bond distance was optimized.
Thanks.
Okay, thank you very much.